Today we'll be going over complex derivatives. Before watching this video, you should be comfortable with the basic derivative rules. We'll briefly show the rules here, but the primary focus of this video will be to show how multiple rules might be required within one problem. If you struggle with any of these rules, you should study a few examples before proceeding. Here you see the first three derivative rules, or what I like to call level 1 derivative rules because they are the most straightforward and typically the set you learn first. A few things to keep in mind is that d over dx is just another notation for derivative, same as the prime notation you might be more used to. C is the notation for a constant number, x is the notation for a variable, and n is the notation used for an exponent. You can read each of these rules as a recipe. For example, the power rule might be read as the derivative of a variable raised to the power n is n times that variable, now raised to the power of n minus 1. Try these examples on your own to make sure you're comfortable with these rules before continuing. You can pause before the answers are revealed. Here are the level 2 derivative rules, which are a little harder than level 1. Again, try each of these examples on your own. You don't have to be able to do each of these with no problems, but at least be familiar with the notations and the processes. The answers will be revealed in a moment. Finally, here are the level 3 derivative rules, which tend to be the rules you learn last, although they're about the same difficulty as the level 2 rules. These 4 rules are really just 2 rules, one dealing with exponential functions, the other with natural logs. The reason there are 4 instead of 2 is that these rules are further broken down into a rule for the simplest case and a rule for general cases. The chain rule for exponential functions and the derivative of a natural log of a function are the more general rules, while the other 2 are rules for the simplest cases. While it can be helpful to see the simplest cases, the rules that deal with the general functions are far more valuable and versatile than the specific cases. Again, pause here to try each of these examples on your own before proceeding. Here are the 5 steps we will use to guide us in understanding complex derivatives. First, we'll identify the outermost structure of the function. Second, we'll rewrite the function in terms of mathematical notation. Third, we'll identify the rule we need. Fourth, we'll match the symbols to parts of the function. And fifth, we'll use the derivative rules that we just finished going over in order to complete the derivative. Identifying the structure of a function is often the key to understanding how to take the derivative of a more complex function. So let's take a moment to look at some examples. Remember that we're trying to identify the outermost structure that applies to the entire function, not just one part. So here we have 2 functions that look very similar, only in the second example, the 3x squared minus 4x plus 3 is raised to a power, so you might think the general power rule comes into play. But recall that we're looking for the structure that applies to the entire function, not just one part. So in that case, we see that this is still just a multiplication of 2 smaller functions, regardless of what those functions are, and we would use the product rule here. In this second example, we see 2 similar functions again, with the bottom function having a natural log in the denominator. But does the natural log apply to the entire function? No, it only occurs in the denominator, so both of these have the same basic structure, one function divided by another function. This means we would use the quotient rule for both these functions. In the third example, we again see 2 similar functions, although in the second, the exponent becomes a little more complex, with the product of 2 smaller functions. Is this an application of the product rule? While we might have to use the product rule, recall that in our first step, we're simply identifying the structure of the entire function. And here, the multiplication of the functions only occurs in the exponent. So if we step back a bit, we can see that essentially this is an exponential function, and we would use the chain rule for exponential functions, since our exponent is not just a simple x. In this last example, we see one function that is simply the natural log of a smaller function, and another function that has both division and a natural log. While both the division and the natural log apply to all parts of the function, the natural log is outside the division in the second example, so the base structure is the natural log, not the division. Recall we're looking for the outermost structure in the first step. Now that we've gone through these examples, let's talk about some similar functions that have different base structures. Recall that we are trying to identify the structure that applies to all parts of the function. If there's more than one structure that applies to all parts of the function, we are looking for the outermost structure. Here we have a product of two functions wrapped in an exponent. Both the multiplication and the exponent apply to all parts of the function, but the exponent is the outermost function, so this would be an application of the general power rule. Here again, the division and the natural log both apply to the entire function, but the natural log is the outermost function, so that's what we identify as the base structure. In this example, the exponential function with the e is in both parts of the function, but the exponents aren't the same, so only the multiplication really applies to both parts, and we would identify the base structure here as multiplication and use the product rule. Finally, in this function, while the natural log appears in both the numerator and denominator, this is different than having the natural log outside. The natural log cannot be factored out like a common number or variable, which you can test for yourself by seeing that the natural log of 3 divided by the natural log of 2 is not the same as the natural log of 3 divided by 2. Since this is the case, the natural log doesn't really apply to the entire function, but rather to the numerator and denominator separately, and thus the underlying structure is division, not natural log. Now you should have a better understanding of this first most crucial step of understanding the underlying structures of many different types of functions. It's challenging to identify all types of complex derivatives you might run into, since there are infinite possibilities. However, students tend to have difficulties when more than one rule is required in a problem. So here are 4 examples taken from the examples we just talked about to show you how to tackle complex derivatives using that 5-step process. We'll go through the first 2 examples together, step by step, and the last 2 you'll have a chance to do on your own, and then check your answers. It might be helpful to print out your formula sheet with all the derivative rules we discussed in the beginning, or have it up on your computer as a reference as you watch this video. So let's start with step 1, which is identifying the outermost structure, which is multiplication. If you have any questions about why it is multiplication, go back in the video to where we covered how to identify the underlying structures of many different functions. With step 2, we'll rewrite that in terms of mathematical notation that matches whatever structure you have. Some students avoid mathematical notation because it looks complicated, but the truth is that familiarizing yourself with the mathematical notation can be an advantage because you can use the formulas directly on your formula sheet to decipher derivatives instead of having to memorize all the rules. You can do this step in conjunction with step 3, which is identifying the rule that matches the structure. We have multiplication that leads to f of x multiplied by g of x, which is the mathematical notation for the product rule. Now we match the different parts of our function to the mathematical notation. The first function is 24x minus 16, and the second function is 3x squared minus 4x plus 3 cubed. Remember that the exponent stays with the second function because we're treating both the function and the exponent as one unit. Step 5 is using the derivative rules to actually do the math. Here's our recipe and here's our equation. Notice the different colors for each of the different functions. Now we just follow the recipe, but we're missing 2 components, g prime of x and f prime of x. Remember that the prime notation is the same as saying the derivative, so the recipe is asking us to take the derivatives of the individual components. To do that, we will write down the 2 components we already have, and then take the derivative of each, being sure to label everything clearly. While getting f prime is pretty easy, getting g prime involves using the general power rule. Pause here and try getting these components on your own. So here are the answers to those 2 mini problems. Now we have all 4 components and can follow the recipe to put them back together. The colors are there to help you identify each of the different components. While the different colors aren't essential to this process, writing out the 4 components separately is far easier than trying to do this all in one step, so I highly recommend doing it this way. Now we have our answer. Don't worry that this looks a mess because there's no reason to simplify it. The only reason to simplify is if you're asked to do so, or if you're using the derivative as part of a larger problem. But it's unlikely that a function of this complexity would be used in such a situation, so we can stop here. Let's do the second example. The outermost structure is division, which we rewrite as f of x over g of x, and which matches the quotient rule. Now we match the different components. And now here's the recipe for us to refer to. Similar to the last problem, we're missing 2 components of the recipe. so we need to find those by taking the derivatives of the f of x and g of x components separately. Note that you'll need the natural log rule to find the derivative of g prime of x. You can pause here and try to do these smaller derivatives on your own. Finally, we put all the pieces of the recipe back together. Again, don't worry about simplifying. The goal of this video is to get you comfortable with the structure of complex derivatives. It's doubtful you'll see anything this complicated used within a larger problem. By now you understand the steps, so here's the first of 2 problems for you to try on your own. Then you can check your answers. Here's the solution to the first problem. Here's the last example for you to try on your own. To recap, in this video we learned how to use the 5-step process to getting a complex derivative. We also learned how to identify the base structures of complex functions, and finally we learned that it's only necessary to simplify if the problem you're working with specifically asks you to do so, or if the derivative you're getting will be used in the context of a larger problem. Thanks for watching this video, and I hope you now feel prepared to tackle any derivative you encounter.